How is algebra used to find the solution?
How are arrays used in algebra?
What algebraic equation shows that voltage is related to current?
Hey guys, meet Leslie Curtis. She's an engineer here at NASA Marshall.
Thanks, Van. Dr. Gilchrist is right. Mathematics is one of the most powerful tools that we have available to us at NASA. We use algebra almost every day to find solutions to our problems. This is the Icarus satellite that Jane told us about. It uses solar cells to charge its batteries. Solar cells, which convert sunlight into electricity, are arranged in a pattern called an array. One of the ways that equations can be written in algebra is also called an array or a matrix. Actually, they look a lot alike. Let's compare them. Here's an example of an array used in algebra. Notice the pattern of rows and columns. Now here's a picture of a solar array. See the rows and columns again? Let's use the solar arrays on the Icarus satellite to do a simple math problem that the students at the University of Michigan were faced with. Then let's compare solar arrays with algebraic arrays. The Icarus satellite uses 12-volt batteries. Voltage is a measurement of electricity. And if we use a solar array to charge our batteries, we know from science that we need to have a solar array voltage that is slightly higher than the 12-volt batteries. So let's say 15 volts. To calculate the number of solar cells we need for the array, we use algebra. And since each Icarus solar cell provides 0.5 or a half a volt of charge, how many cells do we need for our solar array to produce the 15 volts? If we solve for C, which stands for the number of cells, we see that it will take 30 cells to give us 15 volts to successfully charge the batteries. From this information, we can arrange our solar cells in a solar array pattern.
Cool, like 10 cells wide by 3 cells high?
Or 15 cells wide by 2 cells high.
So you see, when scientists are trying to calculate complicated equations, we often write them in the pattern of an algebraic array.
That's great. So you use patterns and algebra to determine the amount of solar cells in an array. But let me ask you this. How long does it take for solar cells to charge Icarus's batteries?
Well, that question can be answered using algebra also. We know that the charge on the Icarus satellite batteries is related to current and time. Current is another measure of electricity which is expressed in units called amperes, or amps for short. Now, to calculate the amount of time needed to charge the batteries, we use the following equation. Charge is equal to current times time. Since we want to know the length of time needed to charge the batteries, we can rewrite the equation as time is equal to charge divided by current. The Icarus satellite batteries have a maximum charge capacity of 2.5 amp hours. A typical charging current that we might use to charge the system is 0.5 amps. So if the charge is 2.5 amp hours and the current is 0.5 amps, the equation can be written this way. Time is equal to 2.5 amp hours divided by 0.5 amps. Solving for time, we can see that the time required to reach full charge on the system is 5 hours.
Okay, let me see if I got this straight. We use voltage as a way of measuring electricity when we're talking about the solar array, and current to describe electricity when we're calculating the time it takes to recharge the batteries. But how are voltage and current related?
Voltage and current are related by the simple equation V equals IR. V stands for voltage, which is usually measured in volts. I is the current, which is usually measured in amps, and R is called the resistance. The resistance is measured in units called ohms. And the equation V equal IR is actually called Ohm's law, after G.S. Ohm, a German scientist, and the unit of resistance was named in his honor.
You just wouldn't believe the resistance I got. Shocking.
You know, I think it's pretty sweet that the university students used algebra to work with NASA on the ProSEDS experiment.
Yeah.
But I don't really get the volts and amps and resistance.
Oh my.
Volts and amps and resistance, oh my.
Get it, Dorothy? And,
I get it.
I just couldn't resist. Nor could we resist the chance to meet some students who teamed up with NASA Connect and are wired for today's web activity.